Let us discuss about Coriolis mass flow meter. By using this flow meter, we can find mass of the flowing fluid, or we can find density of the flowing fluid, or we can find the temperature of the fluid also. If we know the mass and density values, we can find the volume of the fluid also, how much volume is flowing in the given pipe. So by using this formula, as we know, density is rho, density is equal to mass by volume. Okay, if you know mass, we can substitute here, density we can substitute here. By using this formula, we can find volume is equal to mass by density. So we can find the volume of the flow also. Here, before discussing about the working of the flow meter, here we will see what is the Coriolis effect. Because in this flow meter, we are taking this Coriolis effect for measuring the mass flow. Okay, so let us take what is the Coriolis component or Coriolis effect. First take what is Coriolis effect. Coriolis is scientist name. He is a mathematician. He has invented this effect in 1835. According to him, as we know, Earth is wider at the equator. Here at the wider part, angular velocity is more compared to the poles. At poles, velocity is 0. Okay, so here for finding this effect, what he did means, he is taking one bullet, okay, and he wants to shoot in the north direction, in this direction. His target is in the north direction. What he did, he shoot the bullet in the upward direction, okay, but the bullet is coming, the projectile of the bullet is coming like this. The path of the bullet is in this direction. Why it is coming in this direction means, as we know, on this equator the velocity is more, angular velocity. If you are shooting from higher velocity to lower velocity, so it can't move in the perfect north direction, it is turning like this. Okay, so this effect is called Coriolis component. And here similarly, if you are shooting from pole to south, let us assume in the next case, if you are shooting the bullet from pole to south direction, in the downward direction, as we know, at pole velocity is 0, from 0 velocity to in the direction of higher velocity. The projectile of the bullet will come like this. Okay, instead of going in south, the bullet is going in this direction. Okay, this effect is called Coriolis effect or Coriolis component. Because of this Coriolis effect, the wind direction is changing and the tides are coming, the direction of the tides are in different direction in the sea. So by using this effect in weather forecasting also, they are telling where the rain is coming and where the climate is clear, like that. So this effect is very important. This mass flow meter, we are using one U-shaped flow tube for measuring the mass of the flowing fluid. Okay, we will discuss all this in description as well as in working operation. Let us take the basic principle of this flow meter. Here written Coriolis effect measures the mass flow. So here we are using the Coriolis effect for measuring the mass flow. Here how this Coriolis effect is coming. Here, as I told, we are using the flow tube, okay, like this, for measuring the flow. Okay, here whenever flow is coming inside the pipe, so weight is coming in downward direction. Here also in Coriolis component, we are taking when the weight is coming downward, the projectile is in this direction. Okay, so this pipe or this hose will twist. Okay, so it is initially like this, it will twist like this because of projectile of the weight. And here flow is going upward. Whenever it is going upward, the projectile will come like this. Okay, the path, because of the fluid in upward direction, this side of the pipe will also twist. So the entire flow tube will twist. Okay, instead of in the same parallel plane, it will twist like this. So this twist is coming because of Coriolis effect. This Coriolis effect will measure the mass flow of the flowing fluid. Okay, so this is the main basic principle of it, and we will see how can we measure the mass flow in the working operation. Let us take the description of mass flow meter. Here we are using three main parts in the flow meter. So here I did the diagram of the flow meter. Okay, this is the front view of the flow meter, this is the side view. Here we are using, first part is U-shaped flow tubes. Here we are using U-shaped flow tubes. Two tubes we are using. We can call it as hose also. Okay, two pipes or flow tubes we are using here. So these are connected parallelly. These are connected like parallel tubes. Okay, here one tube, here one tube. Okay, we are connecting these two tubes to the flow pipe. Okay, in which we have to find the mass of the flow. And then second one is sensor assembly. We are connecting sensors here as shown in the diagram. Here one sensor, here one sensor. So this is a, if flow is coming, it is coming in the downward direction like this. Okay, at input one sensor, and then water or flow is moving in this direction. At output one sensor, and again flow is going in this direction. Okay, for each tube we are keeping two sensors. At inlet hose one sensor, at outlet hose one sensor. For the two tubes also, at inlet way we are connecting here one sensor, here one sensor, and the outlet also here one sensor. For the pipe which is invisible, I did with dots, here one sensor. Okay, so we are connecting the sensors at inlet and outlet. And then next one is electronic unit. Okay, so whenever water or flow is moving in this flow tube, the sensor will take the signal and it is giving it as output electrical signal like this. Okay, it will give the display. So for taking the effect of sensor, we are keeping the electrical unit. Okay, for studying the output in the form of sine wave like that. Okay, so there are three main parts in it. Here one more part is important. As I told, we are using two flow tubes. Okay, these flow tubes has maintaining some distance. Okay, whenever flow is going inside this, they will oscillate. Okay, whenever they are oscillate, they will come in each other. Okay, so for avoiding it, for keeping the distance between two flow tubes, we are connecting one magnet here. Okay, same magnet here also, same magnitude of magnet here. Two magnets we are connecting here. Okay, let us assume this is the north pole, this is also north pole. Okay, if you are keeping same magnets, okay, same magnets can't attract with each other, so that they will keep distance between the tubes. Okay, if you are using, this is north pole, this is south pole, both will attract. Okay, both pipes will come like this. For keeping the distance between two pipes constant, okay, we are keeping the magnets here one magnet, here one magnet of same magnitude. Okay, these are the main parts in the description. Let us take the working operation of this flow meter. This arrangement, this is the front view, this is the side view of the flow meter. We are doing the working operation in two parts. First, we are not giving any flow to the flow tube. Okay, so there will be no flow initially in the first case, and we are studying the output without flow. And in next case, okay, second case, we are giving the flow and we are studying the output effect. Let us see how the two effects are coming, without flow and with flow. In first case, without flow, just we are connecting the flow tubes here to the pipes. Okay, like this. Here, when there is no flow, as I told, these are the hose, okay, pipes of small diameter. So these are vibrating or these are oscillating. Okay, so these two pipes or these two flow tubes will oscillate in opposition to each at natural resonance frequency of the tubes. Whatever frequency it is oscillating, the same frequency the another tube is oscillating. Both frequencies are same if there is no flow. Okay, if both are oscillating at the same frequency, we can call it as it has resonance. Okay, so if these two are oscillating, the sensors will take that oscillations and it is giving the output as electrical signal. Okay, so here, as I told, this is the input sensor, this is the output sensor. Okay, if we are taking input signal here, okay, without flow, it is giving the sinusoidal like this. Okay, this is the y-axis and this is the time on the horizontal axis. Okay, the signal is coming like this. This is the input signal. If you are taking the output signal, let us assume it is starting here. This signal will also give the same sinusoidal way. Here both signals are coinciding with each other because of the same frequency of the tubes. Okay, in this case we are calling this is a synchronized way. And here next, take the next case, use some flow, the flowing fluid, whatever fluid we are taking, supply that fluid. So this mass of the fluid we have to find, give the flow, so it is entering like this and it is coming in the upward direction like this. And here also if you are taking in the side view, water or flow, any flow, whatever flow we are giving, it is dividing here half, yeah, and remaining half in this case. Okay, again it is coming out like this. Okay, whenever flow is entering, okay, so here it is coming in this direction in input hose and it is going in this direction and in this direction, okay, at the output pipe. Because of downward flow, these flow tubes will twist, okay, in this direction. They will twist in this direction, little twist will come. For the upward direction, they will twist in this direction. They are oscillating already without flow only, but because of this flow, yeah, instead of oscillating, they will twist. Okay, let us take, they are oscillating, again they will twist like this. This twisting movement we are calling because of Coriolis effect. Okay, if we are taking the output signal at inlet sensors and outlet sensors, so let us take at inlet sensor, we are getting the sinusoidal way like this. Okay, because of twist or because of Coriolis effect, the output signal is coming like this, red color one. Okay, red color signal is the output signal, but both signals are not coinciding. Okay, why means because of the twist in the flow tubes. Why twist is coming means because of Coriolis effect. The change in the waves, we are calling it is a phase shift. Previously with no flow, both are coinciding. Because of flow, they are getting the distance, some distance. We are calling it is a phase shift or horizontal shift. We are taking this phase shift in terms of delta t. T is the time on the horizontal axis. This is a delta t. So this delta t will measure the mass of the flow inside the pipe in the calibrated form. Okay, so we can see delta t value on the display board. So here we are calling both signals are non-synchronized. They are not coinciding, input signal and output signal. These are the non-synchronized waves. So this is the main working operation of this flow meter. Here we can compare this flow and the flow tubes with this diagram. Let us take the, as I told, these flow tubes are oscillating. Okay, whenever flow is coming, without flow also they are oscillating. Here I am taking, instead of this flow tube, I am taking spring. I am keeping some mass. Mass indicates the flow here. Let us assume we are keeping small mass. With small mass, this spring is vibrating more. It is getting more vibrations. Okay, if small mass is entering, it is getting more vibrations, this hose or tube. If you are keeping bigger mass, okay, or more density mass, it has getting very less vibrations. Okay, so vibrations we can call it as frequency. Okay, frequency is less for the big mass. We can call it as this density and frequency are inversely proportional to each other. Okay, if you are taking bigger density, less vibrations, smaller density, more vibrations. Here we are getting one equation. Rho means density. Density is proportional to 1 by f square, where f is frequency, okay, of this spring. So remember this equation for the calculation part. So this is the main working operation of this Coriolis mass flow meter.